So hello everybody and welcome back to another RUS Copernicus webinar. My name is Miguel Castro and today I will be guiding you through another topic. This time will be air quality monitoring with Sentinel-5P data. So before starting, let me tell you the objectives of this session. You will learn two main things. First, how to monitor air quality with Sentinel-5P data, and second, what is the RUS service and how it can help you processing Copernicus data in your projects. So just before starting, be aware that this webinar is being recorded and that you will be able to repeat this exercise by yourself. I will give you more information about that later on during the exercise. So let's move on and have a look very quickly to the outline of this presentation. We will first of all have a look to the study area. We will then cover very briefly the use of remote sensing for air quality monitoring from space. We will then spend some time introducing the Sentinel-5P satellite, and then we will very briefly describe the RUS Copernicus service, which is hosting this webinar, and we will use the RUS Copernicus virtual machines to run the exercise of today. At the very end, depending on the time we have available, we'll have a Q&A session that will last for 20 to 30 minutes. So let's move on and let's start by having a look to the study area. So this time we are not focusing our analysis in a specific area, but rather we are focusing our methodology at the global scale. We will take advantage of the characteristics of Sentinel-5P that we will describe later on and run this exercise at the regional and global scale. So let's move on to the background of the air pollution phenomenon. So air pollution is a global environmental health problem that is responsible for millions of people dying every year. From smog hanging over cities to smoke inside the home, air pollution poses a major threat to health and climate. The combined effects of ambient and household air pollution cause about 7 million deaths every year, largely as a result of increased mortality from stroke, heart disease, chronic obstructive pulmonary disease, or lung cancer, amongst others. Air pollution in cities are mostly a mixture, some visible such as dust and soot, but many invisible such as very small particles and gases. The more visible components are evident, the smaller particles and gases can be expected. Pollution is classified either as primary or secondary. Primary pollutants are substances directly produced by a process such as the carbon monoxide gas from a motor vehicle exhaust. Secondary pollutants are not emitted, rather they are formed in the air when the primary pollutants react or interact. Ozone is an example of a secondary pollutant. Some of the main air pollutants are carbon monoxide, sulfur dioxide, particulate matter, oxides of nitrogen, or ozone if it's tropospheric. And just to give you a final number of the importance of reducing air pollution, according to the World Health Organization, 91% of the world population, so 9 out of 10 people in the world, live in a place where the air quality exceeds the guidelines of this international organization. So let's now move to the remote sensing background behind the use of satellites for air quality. So it is clear that something has to be done to reduce the impact of air pollution, and governments and decision makers rely heavily on satellite data such as the one provided by the Copernicus Sentinel-5P mission, but also they rely on computing models to show how pollution accumulates and how it is carried in the air. In this way, they can develop appropriate mitigation strategies. Satellite remote sensing is certainly a valuable tool for assessing and mapping air pollution due to its major benefit of providing complete and synoptic views of large areas in one image on a systematic basis. So let's now spend a little bit more time on the Sentinel-5P mission. I want to spend this time, since I guess this is the first time you are dealing with this data, and since this is the first RUS Copernicus webinar dealing with Sentinel-5P. So, the main objective of the Sentinel-5P mission is to provide global information on a multitude of atmospheric gases, aerosols, and cloud distribution affecting air quality and climate. Launched in October 2017, Sentinel-5P aims to fill the data gap and provide data continuity between the retirement of the Envisat satellite, the NASA Aura mission, and the launch of the upcoming Sentinel-5. Sentinel-5 precursor, also known as Sentinel-5P, is the first Copernicus mission dedicated to monitor our atmosphere. The satellite carries the state-of-the-art TROPOMI instrument to map a multitude of trace gases. So, Sentinel-5P provides timely data on a multitude of pollutants that can affect our health. And I want here to describe you very briefly some of them. For example, breathing air polluted with nitrogen dioxide, which enters the air from road traffic and other fossil fuel combustion processes, can cause respiratory problems. Carbon monoxide, which comes mainly from vehicles that do not burn fossil fuel completely, reduce the amount of oxygen that can be transported in the bloodstream. Sentinel-5P will also measure sulfur dioxide, which mainly comes from industrial processes and motor vehicle emissions, but can also be in volcanic plumes. Again, this pollutant can result in breathing problems and is a precursor to acid rain. Another relevant measurement is methane, which is a potent greenhouse gas trapping about 30 times more heat per mass unit than carbon dioxide. Methane can enter the air from the fossil fuel industry, livestock farming, and rice agriculture, for example, and also as a result of thawing permafrost. The mission will also map a less known pollutant, which is the formaldehyde, which can be released into the atmosphere through wood processing industries and from forest fires. It can irritate the skin and affect the health. And last but not least, ozone. So unlike ozone in the stratosphere, which protects us from the sun ultraviolet rays, ozone in the lower atmosphere can cause respiratory problems and can damage vegetation. Here it forms when nitrogen oxides and volatile organic compounds combine in the presence of sunlight. It is the main ingredient of urban smog, and Sentinel-5P will measure both the good and the bad ozone. So let's now focus on the characteristics of the satellite. In this occasion, we have a single satellite mission. If you compare this to Sentinel-1 and Sentinel-2 or 3, we have a dual satellite, which are dual satellite missions. In this case, we only have one satellite for the Sentinel-5P mission with a swath of 2,600 kilometers. It has a daily revisit time and a spatial resolution of 7 by 3.5 kilometers. And it follows a polar sun-synchronous orbit in loose formation with the Suomi mission from NOAA. And loose formation here means that Sentinel-5P orbits 3.5 minutes behind the Suomi instrument, and the reason for this is that the Suomi visible infrared imager and radiometer provides a collocated high-resolution cloud mask, which is important for the detection and calculation of methane. So let's talk now about the instrument carried by Sentinel-5P. So what sets STROPOMI apart is that it measures the ultraviolet and visible, near-infrared and shortwave infrared spectral bands. This means that a wide range of pollutants can be imaged more accurately than ever before. And with the resolution of 7 by 3.5 kilometers, it has the potential to detect air pollution over individual cities. So let's move on now to the different data products produced by Sentinel-5P. Data products from Sentinel-5P STROPOMI instrument are distributed to users at two levels. We have level 1B, which provides geolocated and radiometrically corrected top of the atmosphere Earth radiance in all spectral bands, as well as solar irradiance. And we have also the level 2 products, which provide atmospheric geophysical parameters. In line with the needs of numerical forecasting systems, level 2 products are to be supplied within 3 hours after sensing. This near real-time service delivers products for ozone, sulfur dioxide, nitrogen dioxide, formaldehyde, and carbon monoxide, as well as vertical profiles of ozone, cloud, and aerosol distribution. In addition to the near real-time service, an extended list of products will be supplied in non-time critical or offline, taking advantage of increased accuracies achievable when specific calibration steps can be made with less constraints in time. So let's move on now that we have a clear idea of what is Sentinel-5P and what are the characteristics of this mission, and let's describe the RUS Copernicus service. By the way, before moving into this, here you can see the list of level 2 products that is available from Sentinel-5P. You see we have a specific product for every gas. And just for you to know what we are going to do today, we will be using the aerosol product and the nitrogen dioxide products. So we will focus our analysis using those two analyses. Stay tuned for upcoming webinars where we will give more information about the rest. Well, so let's move on for the RUS Copernicus service. As you might know, RUS stands for Research and User Support for Sentinel Core Products. It is an initiative founded by the European Commission and managed by the European Space Agency with the objective to promote the uptake of Copernicus Sentinel data and support R&D activities. The service provides a free, scalable, and open platform in a powerful computing environment, hosting a suite of open source toolboxes pre-installed on virtual machines, which allow you to handle and process the data derived from the Sentinel satellites. So what does that mean? Well, with the large amount of data and produced by the Sentinel satellites, the challenge is no longer data availability, but rather storage and processing capacities. So to solve that, RUS offers virtual machines so that you can have the appropriate computing environment to handle the data. In addition, RUS also provides a specialized user help desk to support your activities when dealing with remote sensing data and Sentinel data, and a dedicated training program, such as the webinar you are following today. So you can find all the information about the project and how to register on our websites. I recommend you to check them after the webinar if you want to get familiar about the service and its specifications. And I also want to show you our YouTube channel where we upload all previous webinars. So in a couple of days, you will be able to watch the recorded version of this webinar in the YouTube channel. And by the way, it will also be available in our RUS training platform, together with a document summarizing the Q&A discussion we will have at the end of this session. So let's start after this introduction with our exercise. And for that, let's move to the RUS Copernicus virtual machine, which I have here. So if this is the first time you're dealing with a virtual machine, I just want to give you a brief introduction. This is a Linux-based virtual machine where you have everything you would expect in a regular computer. You have your own internet browser. You also have your file manager system to navigate your folders and the data you have. And you also have a predefined list of software that has been installed. So remember, the RUS Copernicus virtual machines come with pre-installed software, and here you can see some of the icons for some of this software. So the first thing we have to do for this exercise is actually to download the data. We'll be using quite some large list of products, but I will show you how to download the first ones we are going to use. So for that, let's go and open the internet browser. So Sentinel-5P, or the data of Sentinel-5P, are still in what we call the pre-operational hub. It means that it's not still on the on its final location, and that's why we have to go to this specific pre-operational hub. So to access the hub, the first thing you have to do is to log in. You can use the guest credentials that is provided. And once you are logged in the platform, you can start to search for your data. Since we are going to run our analysis at the global scale, we don't need to define any specific study area, so we can just define the parameters we need to search for. So in this case, we open the sign menu and we set the sensing period. In this time, we are going to be analyzing products from the 17th of May 2019. So I will just put the dates here. The next thing we want to specify is the mission, in this case Sentinel-5P. We also want to specify the product type. Remember, I was showing you that today we will be using only the aerosol products and the NO2. If you open the product list, you will see there is a long list of products available for sure. And remember, today we are interested in the aerosol product and in the NO2 product. So I will show you the data download for this one. The same applies for the second one. So we select the aerosol product. For the processing level, it's not necessary, but just for redundancy, we will put level 2. And again, for redundancy, we will put that we want an offline product, so it's not a near real time. So once we have this, we can just search, press on the search icon and look for our data. And here we have the list. So when downloading offline products, what we get is actually the full orbit instead of individual images. And that's why you can see on the map this shape of the products. So in order to download the product, it's very easy, as with Sentinel-1, 2, or 3. We just need to click on the arrow and then save the file. It will be saved, remember, in the RUS Copernicus virtual machine, not in your computer, since we are using this cloud environment. So we have to do this for all the images, so the 13 products. However, to save time, I've done this in advance and we can just move on. So let me close the browser and let's move on. So in this exercise, and to analyze our data, we will use the basic Envisat atmospheric toolbox, also known as BIT toolbox, to analyze the Sentinel-5P data and run our analysis. The BIT project aims to provide scientists with tools for ingesting, processing, and analyzing atmospheric remote sensing data. And the project consists of several components, with the main ones being CODA, HARP, and VISAN. I want here to give you a little bit more of information about VISAN, since it is the platform we will use today. So VISAN is a cross-platform visualization and analysis application for atmospheric data. The application uses the Python language as the means through which you provide commands to the application, and the Python interface for CODA and HARP are included so that you can directly ingest data within VISAN. Finally, VISAN provides some very powerful visualization functionalities for 2D and world plots. So let's open VISAN in our RUS VM. We have it here. And the first thing you will see is this Python shell and command line interface that you can interact with. You also have a starting message. If you are new to the software or new to the data, I would recommend you to go through this. So the first thing we want to do is to explore a little bit the products we have just downloaded. And for that, we go to File, Browse Product, and then we navigate to the specific folder where we have saved the product. So here you can see the list of 13 projects I have downloaded in advance, and we are going to explore very briefly the first one. So I select the first product, clicking Open, and now I have this window appearing here. So once open, VISAN gives you the option to navigate the Sentinel-5P product if you go to the products folder, and also access metadata information, of course, in the metadata folder. The product folder contains data of interest as 2D arrays, such as the aerosol index, the error estimates, the quality index, etc. Within the product folder, you can find the support data subfolder that contains additional and auxiliary data, such as geolocation, flags, lat-long bounds, satellite position, etc. So let's have a look very briefly to the aerosol index, to the first one here. And you can see that in the 2D grid in the array, the first thing we have is invalid data. So this is just because the orbit, the first acquisition in the orbit is just invalid data. But if we go down a little bit, you can see already the measurements. So this gives you already a first look at the data, but of course it's not very intuitive. You cannot make any conclusion out of it. So the second level of visualization that you could do is to plot a 2D graph. So for example, we can go here and just set the parameter for the row and visualize our data as a 2D graph. This already gives you an idea of the variation in the data, but still is not very visual since we are working with satellite imagery, so with images. So what we want to do now is to actually create a visualization of the product. And for that, we are going to close this window here, and back in the command line interface, we are going to use a specific command which is called harpe import. So this command here will create the Python command to perform an import a specific product. So the first thing we have to do is to set the path to the product we want to visualize. In this case, we'll navigate to the product of interest. In this case, it's going to be this one. Then just clicking open. For the operation tab, well, the operation tab gives the possibility to provide a single string where individual operations are separated by a semicolon. However, for this exercise, we will leave it empty since we will explain the operations later on. For the ingestion options, it gives the option to ingest different variables from the Sentinel-5P product to the harpe converted product. But again, for this exercise, we will leave it empty since we will deal with this later on. So once we have our product defined in the file path, we just need to name this product with a variable name. In this case, I'm going to call it S5P underscore aerosol, so AER, and just import. So you have to take into account that the interaction we will have with the software in this exercise is always going to be through code, through a command line interface. So once we have our product imported, in order to plot it, we just need to write a specific tool that is called it's called wplot, and we just write the name of the variable that it's pointing to our product. So in this case, S5P and then AER. And if we do so and click enter, the plot is visualized. So let me just arrange very quickly the layout of my windows to have a better visualization. And here we have. So here you can see the product we have just downloaded, and of course this gives us much more information and gives us the ability to interpret the data in a better way than before in the table or in the 2D plot. So you can see the absorbing aerosol index. You can see different values, and just to give you an idea of how to navigate this plot, with the left click on your mouse you can just navigate in any direction. If you want to zoom in, you can right click on the mouse and just go up or down in order to zoom to a specific area. So you can see already the Sentinel-5P is very good at seeing spatial patterns, and its spatial resolution is helping a lot to identify the pollution in specific areas. You can play a little bit with the visualization of this plot. If you go to view properties, you can change, for example, the color bar, you can change the minimum and maximum values. However, in this occasion I will leave everything as default, but this is completely up to you. So this is just a very brief introduction to the software and to its capabilities to visualize the products, and let's now start our analysis actually. So with the objective to create a world map of the aerosol index, we first need to process the Sentinel-5P level 2 products to keep a single grid per orbit, and to convert the level 2 products into what is called a level 3 product. The conversion is done combining several operators in a single call, and I want now you to pay attention to these steps, since we are going to be repeating this processing during the whole session. So I have a couple of slides to explain you what we are going to do. And let me go back here. So remember always that we are interacting with the software via command line, via specific code that we have to write. Of course, we are giving this code to you already in advance, so you don't need to worry. So the first operator we need to apply, or the first, let's say, tool that needs to be applied to the data, is known as the harpe bin spatial tool. So this tool maps all time samples into a regular spatial lat-long grid for all variables in a product. The choice of the spatial resolution that is set by the lat-long edge step parameter and the boundaries, which are set by the lat-long edge offset parameter, can be chosen by the user, but please note that a higher spatial resolution and a larger area of interest increases processing time. So there's always a balance to be made. If you are targeting a specific study area, which is very small, then go for the full resolution. If you are targeting global maps, be aware that if you don't regrid to a lower resolution, you will have to think about a long processing time. So this is going to be the first operation we will do to our data. You can see here an example of how you set the parameters for this tool. So it's just the starting and end of the latitude and longitude, and then the offset. The second operator we need to apply is the derived operator. So when spatially binding a product with the bin spatial tool, so the tool I have just explained, only the lat-long bounds of the grid cells will be saved in the output product. So to write the lat-long center coordinates of the pixel or of the new spatial grid we are creating in the output, we use the derive operation. And the third operator we will use is the comparison filter, which filters a dimension for all variables in the product, such that the items for which the value of the provided variable doesn't match the expression gets excluded. So it's just a tool that we use to compare specific variable and discard everything that is not equal. So once the concepts of the steps we will combine is clear, and please make sure you are in line with this, we will use the command line tool to combine all of them. So it's not that we are gonna go one after the other, but we will combine them in a single call and process our product. So the command line tool allows to define a list of operations. In our case, the list of operations is bin spatial, derived, and the comparison, to apply to each product using the A parameter. So let me show you what I'm talking about. So the command line tool is called harpe convert. That's how we call it at the beginning. And then we have to set the A parameter. The A parameter specifies that after that we will set a list of operations to be applied to the product. Remember, our list of operations is what I just explained. So we just put the A parameter and we open a quotation. So here you can see, let me highlight this in my presentation. So we put the A parameter, then we open the quotation and we start to write the commands of our tools. In this case, we have the first one. Then to write the second one, we put the semicolon and we keep adding the next one. In this case, the bin spatial. Again, semicolon at the end. And then we put the derived. Once you have put the complete list of operations to be applied, close the quotation in order to make the software understand that this is the end of the tools that have to be used to process the data. Once this is set, the only thing you have to do is to set the path to the input product you want to process. So in this case, we put the path. So in this case, shared training, etc. And then we put the Sentinel-5P product we want to process, and here you can see it. Next, we put the output directory where we want to save the output together with the output name of the result. So in this case, my output directory is going to be this one, shared, training, processing, etc. And here you can see the output name for the product. And of course, we keep the same format for the product. So once we are clear with what we are going to do, let's go back to the virtual machine and let's run this specific command. For that, I navigate first of all to the folder where I have my data. In this case here, this is the data I want to process. I will open the terminal here, so right click, open terminal, and I will just copy paste the code I was showing before. I have it in my aux data folder, so let me just copy paste it very quickly. So this is exactly the same as what I have explained previously on the slides. So you just need to open the terminal in the right folder and write the command. Let's press enter and see the result. Okay, so the result is done, and as you can imagine, the output has been saved in the appropriate folder. So here we have it. It is this one. So once the product has been created, the next thing we want to do is to visualize the product. So the procedure is the same as before. We go to File, harpe import, we specify the file path. So in this case, we navigate to the specific folder and we select the file, and then we just write the output name of this variable. In this case, I'm going to call it AER_level3. So the product is now imported into Visan. Now we just need to write the specific command to visualize it. And for that, we are going to use a specific code just to make sure that we are displaying the right product. If you use, or at least my experience, if you use wplot and just the name of the variable, you will get a different layer being displayed. So you can avoid this by specifying the exact layer of the product you want to display. So here we have the product, and just for comparison, I will put it next to the previous one so that you can understand what we have done. So the idea was to, let's say, reproject the product into a common grid, since our target or our final target is to produce a world map. So we want to have our products in a common grid that covers the whole world, and for that, of course, some resampling has been done in order to merge pixels that were neighboring pixels. So you can see the difference indeed in resolution. You can see that my left product is has a much lower spatial resolution compared to the first one, but that is fine as far as you are targeting a global application. So in our case, we want to produce a world map, so we are not that interested in the details of specific study areas, and that's why downgrading the spatial resolution of the product is not an issue right now. However, if you are targeting a specific study area, you might not want to do that. Again, the spatial resolution is up to the user, up to the application, etc. So this is the result. But what we want to do now, as I said, is to produce a world map. So Sentinel-5P offline products are delivered as single file orbits. And to create a world map using all the products available within a day, they all need to be processed as explained before. So we need to do this for all the files, for all the orbits that were acquired that day. And once they are processed, we need to merge those products and create a final product that is the world map. So once each Sentinel-5P product is processed to keep a single grid per orbit, we will concatenate all the outputs files to create a world map. And for this, we will use a specific tool, a specific operator of harpe that's called harpe merge, which combines multiple products from files or directories by appending them across the time dimension and storing the result into a single output file. So how does it work? Let me go back to my slides to show you the sequence in the code. So the first thing we do is we write harpe merge, which is the keyword for the tool, and then we define a list of operations to apply to the merge products. So that's why in this case, let me highlight it, we have the AP parameter here. So by writing AP, we are saying to the tool that we want to apply a specific list of operations to the merged product, but not to the input products that have to be merged. So in this case, the operations we want to apply to the merged product are intended to properly export the output merged product. The bin operation will average each of the lat-long grid cells over time, and the squash operation will remove the time dimension created by the bin operation from the lat-long variables to have proper georeferenced products for further use in software such as QGIS or Panoply, in case you're interested. So this is what we're gonna do here, and remember, you put the AP parameter, you open quotation, then you specify your tools, which are separated by a semicolon, and then you close the quotation. This is the syntax you have to follow. So once we have declared the tools that we want to apply to the output merge product, of course, we have to define the tools that have to be applied to the input products before they are merged. And there's no surprise here. What we are going to do to the products is the same as we did before. So we put the A parameter, which defines the list of operations to apply to each product before they are appended. And in this case, we are doing the same processing as harpe convert that we did in the previous part. So we put the A parameter, we open quotation, and basically these commands here are exactly the same as what we have put before. And then we just close the quotation. So after this, it's very easy. We just need to specify which are the input products we want to process and where we want to save the output. So for that, we specify that we want to process all the products within the folder. In this case, we specify, we put the asterisk icon to specify that we want to process all the products that start with the following pattern. In this case, we are taking advantage of the naming convention of Sentinel products to identify those. So in this case, we are saying all the products in my folder that start with S5P underscore offline, etc., and then ends by .nc are the ones we want to process. And after this, we just specify the output path for the output product. So this is the output path, and then just the output name and the output format. So once this is clear, let's go back to the virtual machine and run this command. Let's go here. So we navigate to the folder where we have our products, in this case here, remember before we processed this product, now we want to process all of them. So we just right click, open terminal here, and we write the command I've just shown in my slides. So let me copy pasting from the txt file I have here. It's going to be this one. Okay. And let's go back now to the terminal window and just put it back. Okay. So let's run it and let's have a look to the result. It's gonna take like 1 minute, so I just want to take advantage of this time to remember what we are doing. We process one single orbit and we, let's say, resample it or we reproject it into a specific grid, and then we are doing the same for all the products that were acquired on the 17th of May 2019, so that they are all in a common grid, so that we can combine them, we can merge them and create a world map of the aerosol index captured by Sentinel-5P. So once the process will be finished, we will proceed as before. We will go and import the product using the harpe import tool, and we will just visualize that in the visualization tool of vSAN. Okay, so the process is finished, so let's have a look to the result. So I will minimize this, and again we go to File, harpe import, we navigate to the path where the output has been saved, in this case, in this case here, 3, and this one here, global aerosol level 3. So let's import it and let's change the variable name to something more meaningful, so level 3 underscore global. And now we can just again use the specific wplot command to show the result. Again, I'm using a customized command to make sure there's no mistake. Again, it's just based on my experience. If you use only wplot plus the variable name, it will give you the wrong layout. So here we have the world map for the aerosol index on the 17th of May 2019. So let me first of all change a little bit the visualization so that we get a better view. I will go to the to the view properties, and in the color bar I'm gonna change the color bar title to absorbing aerosol index. I will also change the minimum and maximum values to -5 and to 5. Remember, each time you change a parameter in the properties, just click enter to let's say input the parameter to the software. And we can also put a title to the plot, so that would be the aerosol index on 2019 05/17. Okay, so let's now have a look to the data, and you can see that by processing all the file or all the orbit files with the harpe convert command, by let's say reprojecting them into a common grid, we are now able to merge them together and create this world map. You can see, of course, that in the Sahara desert we have a high value for the aerosol index, which makes sense. Also in some cities over China, etc. By the way, just for you to know, if you look in the ocean, we can see that there are some high values appearing, and those are caused by the sun glint, and this can be removed by doing further processing in vSAN by just applying a quality filter. I will not go today that deep into the data processing, since I want to keep it as simple as possible for an introduction to Sentinel-5P data. In the future, we will explore those options a little bit more. So once we know how to create world maps with Sentinel-5P data for a specific product, in this case the aerosol, let's move to the next application. So in this case, what we want to do is to monitor a fire event using the aerosol index. You know already in RUS we've done other webinars related to fire. We've done the fire detection with Sentinel-3 or the burn area mapping. So in this case, a different approach, we will use the aerosol index of Sentinel-5P to monitor the smoke produced by a fire event. So let me introduce you the study area we are going to be working now. So, as I said, taking advantage of the Sentinel-5P temporal resolution, we will now explore the capabilities to monitor a fire event in California, in the USA, using the aerosol index level 2 product. In case you don't know, the 2018 wildfire season was the deadliest and most destructive wildfire season on record in California, with a total of 8,527 fires burning. In November 2018, strong winds aggravated conditions in another round of large destructive fires that occur across the state. This new batch of wildfires included the Woolsey Fire and the Camp Fire, becoming both California's deadliest and most destructive wildfires on record. So, how are we going to process our data to analyze this effect? Well, let's first of all go back to our virtual machine. And the data for this study area has been already downloaded in advance, as I showed at the beginning of this session. And I just want to show you that what I have is basically the Sentinel-5P offline level 2 aerosol index products for that specific location for different dates. So my time series starts in the beginning of November 2018. So this is the image from 2018-11/02, and then you can see I have the same for the day after, the day after, the day after, etc. So it starts on the 2nd of November and it finishes on the 21st of November of the same year. Remember, with Sentinel-5P we have daily revisit time, and this is great. So what we are going to do is to process our products with a similar command line script. So let's process our data, and for that we are going to use a similar code that we have used before. So I will not go step by step as before, since it's more or less a repetition, but I will explain it briefly. I have it here, and what we are going to do is just to copy paste it directly on the terminal. So this is the folder where I have my data. I will open the terminal here, and I will just paste the command. And what the command will do, basically, it's a harpe merge. So remember, we are merging products not only spatially, but also in the time dimension. We are specifying with the A parameter the list of operations we want to run to the products before being merged. In this case, we are specifying a specific study area by defining the latitude, but also the longitude. We are also defining with the bin spatial what should be the size of the spatial grid that we will use to reproject the products. In this case, we are setting 0.1 as offset. Then you can here see the derived operation to derive the center coordinates. And basically after that we are closing the quotation, remember, and defining our input products. In the same way, we are using the asterisk to define that we want to process all the products that start with this specific pattern. And then we just set the output path and the output name for the product. So let's run this and have a look to the result. So again, we process the data in the terminal, and then we visualize the data in the Vision visualization tool. And in this case, we are doing a time series analysis that will allow us to see how the aerosol index is evolving while there are some fires happening in the area. So the process is finished, and you can see it's very fast, but don't be confused about this. It's basically because I'm defining a quite low spatial resolution. If you define something higher, then it will take more time, just that. But just in order to keep this as a live demonstration, I will leave it like that. So let's import the product, and for that I go to File, Harpe Import. I define the file path, the product I've just processed. So in this case, it's gonna be in the processing folder, in the file California, and it's gonna be the first one. And for the name, I'm just gonna call it with an easy name. It's gonna be just fire, and just import. In this case, we can directly use the wplot command it will not create any problem. So we just write wplot and the name of the variable that points to the product and click enter. Oh, sorry, I just put the wrong, it's capital F. Okay, there it goes. So here we have this interactive visualization of Visan. So let me just resize my windows. The first thing we want to do is to arrange a little bit the layout. So first of all, let's go to our area. So you can see that with the study area that we have defined in terms of latitude and longitude coordinates, we have, let's say, clipped the product to a specific area, and that's why we only see this as a result. What we want to do, first of all, is to change a little bit the visualization. So we go to the Properties tab, and in the Color tab, we are going to, first of all, change the number of labels to 5. Press Enter. I will then put the minimum value to -5 again, and the maximum to 5. And next, I will just change, I will define a plot title, and in this case, I'm going to set absorbing aerosol index, and I will just put the band I'm using. So this is 354 and 388 nanometers. Okay. So once we are done with the visualization, we can close it, and now we just need to set the parameters for the time dimension visualization, let's say. So in this case, we want to display the view as a loop. We will set the speed to 1 just to go slow, and we can now press the play button and see what's happening. So you see that at the beginning of November there were no fires, then suddenly the fire starts and the aerosol index starts to increase, of course, because of the smoke and all the particles being released to the atmosphere, and then the visualization starts again. By the way, if you are curious to know which image or which is the date of the image being shown, you can go to the properties, and in the attributes you can see that while the animation is moving, in the date time start parameter you can see the value. So in this case you see 4, the 5th of November, 6, 7, and then the 8th of November the fire starts to be reflected on the aerosol product. Okay, so now you know how to monitor a fire event with Sentinel-5P data, and how the aerosol product can give you actually quite useful information about the status of a fire or the extent of the air pollution. Let's now move to the second part of the analysis. I told you at the beginning we were using two products. One was the aerosol product, the other one is the NO2 product. So NO2, you know already, it's causing a lot of issues in terms of air pollution. And to explore the capability of Sentinel-5P to detect and monitor other pollutants, we will create a daily average tropospheric vertical NO2 column using the Sentinel-5P level 2 NO2 product. It's a little bit of too much numbers, but it's like that. So how are we going to proceed? Again, the data that we are going to use for this exercise, or for this part of the exercise, has been downloaded in advance with the methodology I've shown before. So let me just show you the data. In this case, I have it here in the original folder and NO2. So you can see here I have the Sentinel-5P offline level 2 NO2 products, and you can see the dates. In this case, we are using images or products from the 24th January 2019, so at the beginning of this year. So what should be the procedure? It's again the same thing. We go to the folder where we have our products and we open the terminal here. So I'm opening each time a new session. And now we just write the right code that we need to process our image. And this code is being provided to you. So in this case, here's what we are going to do now. And you can see that it's kind of a repetition of the previous steps. So there's not that much to change between one code and another. And let me show it to you. So first of all, we start with the harpe merge operation. So you know already, if we set the harpe merge, it's because we are going to be combining multiple products. Then with the AP parameter, we define the list of operations that we want to be applied to the output product. You know already the bin operation and the squash operation. Then we close the quotation for the AP. parameter, and we open the A parameter, again with its quotation. And this is a similar list of operations as before. We see the definition of the coordinates. We see that we are applying, in this case, a tropospheric NO2 column number density validity, in this case higher than 75. If you are curious about this is just to remove, let's say, the effect, false alarms, and you can read more about this, and I really encourage you to do so in the Sentinel-5P technical and user guides are available in the ESA website. If you want to know more about the specifications of the products and the algorithms that are being used. Then we are using the bin spatial tool as before. We are setting the size of our grid, and we are using the drive operation to set the central coordinates of the grid. Again, we are specifying the input products in the same way and specifying the output directory with the output name and the output format. So let's run this and have a look to the result. So the process will run, and again we will use the harpe import command line to visualize the result. Okay, so the command has finished, and basically the command, what it does is it builds a daily average world map for latitudes between -55 and 60 of the tropospheric vertical column of NO2 on the 24th January 2019 with full quality data. The value of the tropospheric NO2 column number density validity is set to 75, as it is the recommended pixel filter to remove clouds, snow, ice cover scenes, errors, and problematic retrieval. So that's why we set that value. And again, this is information you can find in the technical guides of the products that are available in the ESA website, in the Sentinel-5P ESA website. Okay, so let's have a look to the result once it has been processed. Let me minimize this, and again we go to Visan and harpe import, go to the path where we have saved the output. In this case it is here, and we are going to call this NO2, and let's just use again the wplot command to visualize the output. So here you can see the result, and you might be wondering, well, it doesn't look that well. There's actually a lot of masked areas, and of course you have to take into account that clouds are everywhere, so of course you will have to mask them, and this is also an issue when doing atmospheric remote sensing. I just want to change a little bit the properties of the color bar. In this case I'm going to change the values of the minimum. I'm going to set it to 0, and the maximum I'm going to set it to 0.00075. You can see the units as being mole per square meter. Well, with this product here, which is basically a world map of the tropospheric NO2 column on the specific date, which is the 24th January, you can see that okay, we have some gaps in the data, but you see, for example, here in China we have an issue with NO2. We have some high values in the north of Italy a little bit. Of course, if you have already knowledge about the NO2 distribution, this can help you interpret the data. If you go to the USA, we can highlight some cities, etc. But of course, this is not what we want, or it's not the end of our analysis. And now we're going to move to the last step of this exercise, where we will build a not a daily average tropospheric NO2 column, but a monthly average tropospheric column. So how are we going to do that? Well, it's going to be a similar procedure. Again, the data has been already processed in advance, and let me show you what we have as starting point. So what we have here in this folder are the products, or let's say the world map that has been produced for every single day during January 2019. So you see I have the world map of the NO2, of the tropospheric NO2 column for the 1st of January, but also the 2nd, the 3rd, and so on until the end of the month. And these products have been produced using the same script that I've shown you before to produce this map here. So basically we've done the same but for all the days. You can see already the amount of data we are dealing with when doing this kind of applications. So what we need now is to kind of do an extra processing step to those outputs in order to merge them together and do, let's say, a cumulative or an average product where we see the summary of the detection of NO2 throughout the month. So all average daily maps of tropospheric vertical column of NO2 for January 2019 have been created following the same method as before. So to continue, we just right-click, open the terminal here, and again we will write the specific command that we are giving to you, and I will explain it as well. And here it is. So we just copy this in the terminal, and we are saying, first of all, we call harpe merge, you know already, because we are going to concatenate several products. We call the AP parameter, again with the same list of operations to be applied to the output product. Then we identify the input products, in this case using the naming that we've been given, that the outputs have been given to in every day, and then we just set the output path and output product. So let's run this. Okay, so the analysis is ready, and now we can have a look to this final result we are producing. So again, we do the same. We go to File, harpe import, we navigate to the path of our output product. In our case, it is here. And now we just give it a name. In this case, it's going to be NO2 global, and we just plot the result as before. So wplot NO2 global, yes, and here we have the result. So before starting to analyze it, let's arrange a little bit the visualization as before. In this case, I'm gonna change again the min and max values of the color table from 0, and the maximum is gonna be 0.000, so 3 zeros, 75. And now you can see, sorry, I'm wrong, actually it's 4 zeros. Yes, exactly, now much better, right? And the last thing I want to do is just to put a title to the plot so that we can identify what this is. So I'm gonna make it NO2 levels in January 2019. So let's remove this, and now we can explore a little bit our image. So you can see already the main difference with the daily product is that by averaging the products throughout the month, we remove all those gaps since we are just taking products from different times. We are combining them in a specific grid that it's not the, let's say, original spatial resolution of Sentinel-5P, but since we are interested in the global picture, so I'm not interested into focusing in Spain and see for every single city where is the hotspot. I just want to see the global trend. I want to see that, okay, in Europe there is an issue mainly in the north of Italy, in the north of Europe. If I go to for example, you can see the Nile River and the Nile Delta as a hotspot also. Well, I mean, you can just see the image and make your own conclusions. You can see in India there's also a big issue. In China, of course, nothing to add there. You can see it. So in this way, we can produce those world maps where we can see in a very easy way what's the distribution and the, let's say, what are the values of NO2 emissions that we are dealing with. And you can imagine for policymakers this is a great information in order to monitor what's the status of the pollutants in a specific city or in a specific region, at the country level, even at the global level. So let's move to the last take-home messages that I want to highlight for you. So with the new Sentinel satellites, the challenge in satellite remote sensing is no longer data availability, but rather how to store and process all the information. In addition to that, it is necessary to explain how the data can be used and support users in their applications. The RUS service is here to solve those problems by providing virtual machines to store and process the data, and by offering a dedicated help desk supported by a team of remote sensing experts to help you in your projects with Sentinel data. So, before moving to the Q&A session, let me tell you again that you can repeat this exercise by your own if you want. You can practice and adapt the methodology to your own application or study area. For that, go to the RUS Copernicus portal, register as a RUS user, and request a virtual machine. During that process, you just need to specify the training code, which in this case it is ATMO01. Again, once you get the access to the virtual machine, you will receive a training kit that contains a step-by-step guide as a PDF document and all the AUX data information we've used during the session. So that's all from my side. Thank you very much, and I hope to see you back in another webinar the next time. Ciao!